CEO of Progold in Zito, Italy, is one of those brilliant, curious people. He has dedicated his life, his business, to understanding and educating others about the possibilities, applications, and the technology surrounding selective laser melting, also known as SLM. Today, Damiano takes a step back from years of research to objectively review this technical revolution that is SLM. Welcome to the stage, my friend, Damiano Zito.
Good afternoon. This year again I'm going to, as Matt said, talking about 3D metal printing. I will use the same way to call, SLM, and I will use another word which is 3D metal printing during my presentation. And I wanted to start saying I want to have fun today afternoon. I have a friend of mine that I met out during the speaker's trip, and we decided to say, okay, not be so too much in trouble when you are at the podium, you have to have fun. And I hope you will have fun. On my presentation, I will talk about why should we 3D metal print a jewelry. We started in research on metal printing in 2009, and we were presenting the last 5 years paper about parameters on 3D metal printing, strategies, how to build the parts, physical characteristics, mechanical properties, and then we were also checking different addition to have a much more laser absorption by the metal powder, and then we check also the particle size distribution, as well the resolution, the supports, and then we decided to say, okay, then we collected all those data, and we want to get value from that data. And let's go to a much more pragmatic stage and see, really, in practice, when it makes sense to 3D print a part. Because it's not always convenient to do, but it's also not technology that makes no sense to be taken into consideration. So, the presentation of today will talk about the strength and the characteristic of 3D metal printing compared to casting. Why casting? In the beginning of the paper, we were thinking, oh, we should also compare with electroforming, or we should compare with stamping, which could be a typical technology that allows people to produce hollow parts. But we decided casting because, according to our data, something like 80% of jewelry produced in the world, whether it's silver or gold, are produced by casting. And this number, on our point of view, is quite solid because it's results of 15 years analysis on the market. So I put also the data, how many customer visits we did to collect that information, how many interviews we did with the customers. And when you have 20,000 interviews where you ask to the customer, what do you produce, casting or stamping? And then you say casting, okay, you take a note. And then how much you produce. All that data together says that 80% of the volume is produced by casting. And it makes sense to focus on benchmark with the most common process, whether it's casting universal or without stone or with stone. Every year I used to put a video that most of you is tired to see. And it's an animation to show how 3D printing works. But now I decided to put a movie, a video of a real printing. Here we have platinum 950. It's a bangle. The data are coming from the computer and sent to a laser, and the laser is scanning a powder bed that is on building platform, which is this round one, and the laser is melting every single element. the process after the first layer or the next layer melting, the building platform is going down. Now maybe you can see a little, something like 20, 30, 40, 50 micrometers, sorry, and then the lasers start again. I cut the audio because there were people talking in the back. So let's start with the geometries. In jewelry, generally, you have two possibilities. Or you do solid parts, you do by casting, or you do teeny hollow, by stamping, by electroforming. But if you want to do something in between, you can use casting. Then you have to cast in two parts, and then you have to assemble. Or if you want to do something hollow, you have to do by direct casting. Let me say something more. I will talk today about direct casting and traditional casting. Every year I explain what I mean with these two words. Because during the speaker's trip, I was talking with Nancy, and she told me that maybe direct casting has another meaning, and I should call direct lost box casting. That make much more sense, because direct casting is much more something historical that is no more used today. Anyway, in that case of direct casting, we have a part that we have a pattern that is produced by 3D printer in wax or resin, or traditional casting is something done where you produce the pattern injecting the wax into the rubber mold. In that case of direct casting, you can do a monolithic part, but you have to make some holes from where the investment is going in and going out after casting. The biggest problem of assembling, in case you do two parts of casting, is the soldering line. One more thing, 3D metal printing is focusing only on one segment nowadays, only on high-end jewelry. And the high-end jewelry hate the soldering line for two reasons. The first, the color. It's not easy to get the right color, and it's visible. If you watch at the naked eye, at 30 centimeter, maybe you don't see, but if you watch with a loupe, then you see, and they don't like it. Here we have an example of a white gold soldering line that when you are able also to match the color, then always there is something like a depression on the soldering, because the abrasion is different during the grinding and polishing process. And then, most of you knows that rose gold is one of the most difficult color to match with solders, except if you use laser. But laser is not able really to do a deep soldering. And this is the trend, how in high-end jewelry segment, the one doing only 18 karat high level, how the red gold share changed in the last 7 years. From 26% up to 58%. This is also our data. We have the most famous company in the world. Most of them, they are mainly doing rose gold. This is the time of rose gold. 10, 15 years ago was the time of white gold, but now is the time of rose gold. So if rose gold is a problem, having a monolithic part is a value. And this value we can count, we can have evidence every day when we have customers that they decide to 3D print the parts just to have not the soldering line. Let's move to the thickness. That is one of the issues about 3D metal printing. In case of traditional casting, it's very common if you have a teeny part, when you extract from the rubber mold, then the deformation is always behind the corner. Or if you have to inject something very thin, then it's very easy that you increase too much the pressure and you have rubber swelling, and the size of the wax is anymore the one that you were looking for. Or in case of direct casting, you have a problem that the polymer used, or whether it's wax or resin, they are not able to be really removed. And sometimes you have some residual which are affecting the form filling capabilities. So you have some missing of metal. Another important issue when we talk about thickness is the surface extension. Easy to reproduce something thin but very small, and much more difficult to produce a very wide and large surface, like a hollow ring or hollow earring. So, in general, when we talk about casting, a thickness of 0.4 millimeter is common. Going down is quite difficult, not because of casting problem, but because of wax, because it's difficult to make the waxes thinner than 0.4. And then if the surface is getting bigger, then you have to consider a much thicker cross-section. Then, in case of direct casting, no problem, because you 3D print the pattern, and then you have a very thin wall or thin details, but then you face the barrier of casting problem. In case of 3D metal printing, there is not this problem, because of you go to 0.2 millimeter, this is standard thickness that you can print in case of gold or titanium, but then when you go for platinum, for example, you can go down to 0.15 millimeter for whatever is the surface size you are going to reproduce. So this is one of the best path that we should walk through to understand, to take advantage from 3D metal printing. Here an example of a titanium part with a very thin wall and very extended wall that can be easily produced by 3D metal printing. Here I put the resolution. Every year I was not talking about the resolution of printers, and I was talking about layer thickness, spot size, trace, melting trace thickness, vector thickness. Here I just put the XY resolution. In case of gold is something like 120 dot per inch, and in case of platinum is a bit more on an XY plane. In case of Z, then we are much more resolute because we are able to build parts at 20 micron. So the resolution is quite okay on Z axis. Then another thing that we were collecting from paper presented some years ago was the dimension, the dimension consistency. And we were measuring this part of where the stone is going through. That one was the sample. And are the nominal value. In case of 3D metal printing, we had something like a standard deviation of 3-4 micron, plus minus. And in case of direct casting, we were in a similar condition. The difference was that in case of 3D metal printing, we had the nominal value that was in the range of the standard deviation in 2 cases. But I don't see really some advantage here because even casting is quite good. So the value is not here. And then in both processes, you have to have something that the people doesn't like. In case of casting, you have the feeders, so the screws. In case of 3D printing, you have the sockets. In this picture, we show the same ring that in case we produce by 3D printing or by casting. The contact surface in 3D printing is much lower in that case, and in casting is something like double. But in casting, the contact surface is equal to the total surface interested by the screw. In case of 3D metal printing, we have lower contact surface, but in a wider surface. So, some other things that we can say. Very often, what is not printable is castable, and what is not castable is printable. It's not a technology that makes sense to print what is possible to cast or to cast what is possible to print. In this kind of design, the left one that is not printable because the lamella that we have should be full of supports, And on the right side, we have a casting part that has something like 10 isolated volumes that need to be feed with feeders. So we should be in that condition. It makes no really sense to make a casting part in that way because it's easy to print that one, but easy to cast the one on the right. Here we have an example of a typical surface when you have heavy supports or light supports. What the difference to decide to have heavy or light supports? That is a reason of doing practice and try to fix and figure out which is the lowest quantity possible. But what is a big difference between casting and 3D metal printing is that in casting, if you have a very heavy rings and a sprue of 5 millimeters, then you have to reshape the surface. In this case, the surface is still there, and you can be guided to just remove by bringing the supports, which are quite small. Anyway, the people who are on high-end jewelry, they don't care very much, because really they have to take care of the pieces one by one, grinding with a micromotor, and it's not something done automatically. Let's go to have an overview about the typical defect in the two processes. In case of 3D metal printing, we can have gas porosity, like we have in casting. A typical problem comes because of we have some entrapped argon on the powder and during the melting, but typically the gas porosity in 3D printing is not always on the surface, very often is on the core of the material. Here we have a cross-section of the typical standard that we were using to looking for the proper parameter for the casting, for the printing strategy. In case of casting, we can have a very big gas porosity. I put the worst piece I had. And in case of shrinking, we have no shrinkage porosity in 3D metal printing. But we have sometimes some lack of metals because of wrong printing strategies. So in that case, the one there is because the laser was not scanning that point because maybe the scanning speed was too high. Then, okay, this is a typical shrinkage porosity in casting. Then another defect that we could have on 3D metal printing, always connected to the strategies, is in case you do not overlap the melting trace, then there are some lack of melting in the border of the melting trace. And then talking about some other minor defect that could be in one process or in another one. The carbon contamination is something that can occur only in casting, not in 3D metal printing. Investment inclusion is only in casting. Alloy contamination can happen in both because of mixing of crucible, you don't use the proper one, the clean one, and it can happen also during the production of powder. A biggest problem in 3D metal printing is the powder contamination. Most of people, there are some that say that their printer, that you can use different powder. Once we did, and we were using the same powder, then we had a problem with fineness. Because we were using the batch before platinum, and then we did gold, and then the fineness of gold was going down 750. Why? You have to imagine that in the printing chamber, there is always a gas flow. And the gas flow is bringing out all the smoke that's happening during melting, and also some very small particles are going out. All the pipes around the chamber are full of powder, okay? So if you want to really clean, it's not enough to clean the chamber. You have to somehow, at least with the printer we have, you have to disassemble the printer and imagine that our printers are on the scale, because we know the weight when they were new, and we are keeping tracing the weight in order to be sure that all the powder is of one kind of alloy or another one. Even if 2 years ago we decided to have one printer for one alloy, and we decided to have a strategy to have only that alloy, and if any other inquiry comes, we don't care, because it's really a nightmare to change the powder. I think that is one of the biggest limits at the moment with the printer that we have. Then wall failures, when the supports are not enough, then you can have some problem of some failure on the wall fall down and the part is not well reproduced. And in case of casting, and you have all the problem connected to the patterns, so bubble in the works and so on. Let's go to now the real value or the real reason why we should consider to print a jewel. If you watch on traditional casting or direct casting, you can melt only a very traditional alloy. You can use copper, zinc, nickel, palladium, silver, germanium, indium, gallium, silicon. But then if you look on 3D metal printing, since you have to consider that you can blend the powder and you can have a homogeneous powder done by particle of two different alloys, of two different materials, this is a very big advantage or big opportunity for the future. I think that today is not really ready, even if last year we presented a paper, but it's just starting. It could be, but I don't think that it should be something interesting very much today, or a reason why to go for 3D metal printing. We were able to print a nice gold niobium alloy and nice gold titanium with a very, in case of titanium, very nice yellow index 12 and density around 30%, less than palladium white gold. So the only thing that need to be fixed is the fineness, but not because the fineness was not okay. How to fire sell a gold titanium alloy? We have no way to understand. The ladies seated there, she was trying very hard, but we did not succeed. So we have to change the topic of our paper on the way to go to send the paper to the Santa Fe Symposium, and because really we wanted to go ahead. But we thought, for what reason? To go too deep, maybe we are too far from reality, and there is value to collect now. About residual porosity, we spoke several times during the past years. What I can say, even this one is not a reason to 3D print the parts. Only few inquiries we got that where the customer was not able to cast, that is something that maybe depends from him, that is not able to cast that part. But in general, we just can say that a typical as-cast part and as-printed, after polishing, of course, the as-printed one is a bit more dense than the as-cast one. Here we have data about the measure that we were doing in some yellow gold some times ago. But I want to say, I didn't want to go too deep on the number. I want you much more to trust on the previous year paper presented, because just to give you an idea how many hours we put in this project, I was counting today because I thought, okay, let me say to the people how many hours we put. We just passed 35,000 hours on this project, and I believe that is quite maybe excessive. Let's go to the roughness. This is one of the weak part of 3D metal printing. But we will see that direct casting is not much better. And on the y-axis we have the slope angle. If some of you remember, we were printing some parts with different slope angle, with different angle, because 3D metal printing is having different roughness according to the slope angle on the building platform. And when we are almost horizontal standing, then the roughness of 3D metal printing is very, very high. Something like 4 times higher than traditional casting and 1.5 times higher than direct casting. But then when we go up with the angle, things are going better and better. I changed it, the graph, because the light was not so nice and the color last night didn't work well. So I hope that you are able to see the difference. So what I want to tell you with this slide, the roughness is not much worse than direct casting. And we prove with that 3D image on the surface. This is traditional casting, so very smooth, very smooth. Look at direct casting. So when you see that picture, we are at 500 magnification. You see that, and you watch the 3D metal printing, you see that it's not much worse. It's similar, okay? And the image is quite accurate, because I don't know if you are able to see, but here we have all particles, all spheres, small spheres of powder everywhere. In fact, the biggest reason of roughness in 3D metal printing, and you can see on the image at 500 magnification, is all those particles that are sticking. Because when we scan the outer line, then we melt, and of course the one particle that are touching the melting, they stick the part. About mechanical properties, just I put, because very often people ask me which are the mechanical properties, if it's the same like casting, and they ask, but sintering is the same like casting in terms of mechanical property or properties, and I would love to stress that is not sintering. This is not sintering, it's really melting. The only common thing with sintering is the powder, but what the process is totally different from sintering. In case of mechanical property, I do not see reason to go to 3D metal printing, because we have a tensile strength which is a bit higher. It could be the case of white gold palladium that we were testing this year. And in case of elongation, it's a bit higher. It could depend from a very fine, a much more, how to say, defect-less that 3D metal printing structure is. This is the first thing that I wanted to really point in my today presentation. The volume control. This is a kind of freedom that we should take as an advantage. Really something that we should use as a daily tool to solve problems. Now anymore, you have to consider that you cannot do that part because it's too heavy. I'm talking not hollowing part because you want to do cheap. Hollowing part because you want to do two things. Nice wearability, maybe earrings or whatever else. Or second, you want to have a market position. So having a proper price of the product in the shop. So you can play as you like. We were printing parts, one part I remember, 80 grams. So a ring 80 grams is quite heavy. Then why 80 grams? Because they were not able to do much lighter, that kind of design. But it will not lose in value if it will be 50 grams. Then something nice is this one. In 3D printing, if you do hollow, then you can put maybe some grips to enforce the structure. So the part is much more resistant. And this is something that you can do on 3D metal printing. Of course, you can do also in direct casting. But I don't know if people are doing it. And then the lattice structure. So having a structure inside the pieces, which is really enforcing. The pieces do not sound like empty. They look like just lighter. And this is the thing that I wanted to go today. Once I was in a shop with a friend of mine, and he was buying a pair of good jeans. And he has a size like him. Then he was paying, and then another guy came with the same pair of jeans, but that guy was bigger than my friend, and he was paying the same money. So, and he was complaining with the owner of the shop, because why? He's taking more more material. Why he has to pay the same money? So this happened also with gold. Law is having the apparent volume changing, because all of you knows that on high-end jewelry we do not make the size of the ring. So you make a single model for every single size, because every part of the design has to be balanced with all the other part of the design. And then, so you have the apparent volume changing, but the volume of the part staying constant. So the weight is the same. And here we can see how the gray bars are the volume of solid part. The blue is the volume of the smart hollow part. And the weight, in case of the solid, from the size 48, about the model I showed you, from the size 48 up to the size 60, is going up 8 grams. But in case of 3D metal printing, you can print at the same volume. And the piece appear exactly the same. You have not to make the, I forgot the word Nancy was telling to me, shortcut, undercut is something that is done on the ring, and they are very not beautiful to watch, because you see that he's written, I'm cheap, I want less money for that things. So this is quite important, because of, you have on that triangle, okay, this is all value. I don't believe that if the customer is going and things change 2 grams to 3 grams, they take care. They want to buy that ring, that brand. And high-end jewelry is working that way. This is the driver, not the way. About production lead time, another path. In case of traditional casting, we were considering starting from a new model. So you have the 3D design. On traditional casting, you have to make the masterpiece, whether you make the rubber directly, but then it's quite rough, or you have to cast and then do the rubber. So you have to two burnout cycle. So it takes something like 30 hours from the time that you have the design and the time that you have the part ready. In case of direct casting, it's much faster, because you have directly casting the 3D printed parts. So you have just to have the time of the printer, which is quite fast, to print the part that you want. In case of 3D metal printing, you can have one piece, because we did compare 1 piece, 10 pieces, and 100 pieces. One piece is 1 hour, 1.5 hours. Then if you want to have in rush, you can. And then I don't know if it's the proper word, the break-even point is on 25 pieces. And then direct casting is, in that case, much more convenient. In fact, direct casting and traditional casting, whether you cast 1 piece or 100, the time is more or less the same. Of course, in the case that you want to print something that you can also cast. Because if you have to print something that you can only print, all these things I said, has no meaning. Of course, we have always to remember that we have not to print what is possible to cast. Because the process is much more expensive, has no meaning. It's like to think that you want to go Albuquerque downtown and taking a flight. No reason. You go by walk or you go by car or whatever else. But in the world we have cars and also airplane. You take the one that you need. So the message should be, is one more tool to solve the daily problem. Only this. It's not substituting whatever we have today. About the production capacity, we were doing a benchmark between having a single, in case of casting, 1 wax injector, 1 embedding machine, 1 burnout furnace, 1 casting machine. So we didn't take care about the bottleneck on process. We just wanted to compare. And in case of 3D metal printing, 1 printer. So with the 3D metal printing, you can do no more than 350 grams a day. This is the maximum that you can do. And the part has to be quite particular to reach that volume. In case of traditional casting and direct casting, the quantity is much higher. So, from production point of view, they are much faster. But the thing is, at the moment we are thinking with one printer, but I'm sure that the money invested by, I said several times, the money invested by a company producing chain, that they have 1,000, 1,500 chain machines. They will now have problem to have the same amount of printers. They cost not much more than a chain machine. And they have the same capital invested, so they have a lot of money in gold fixed there for every single chain machine. So maybe the future will be that we will have many printers in one company. And this is something that has to be taken into consideration, even because the return on investment of a printer is much higher than a chain machine. Chain machine, there are many today doing very thin chains, under 50 gram a day, 250 gram a day, and they sell just for loss. No labor, just loss. So the money they bring back home in the evening is not really much if you compare with 3D metal printing. Then we were doing a carbon footprint investigation. So we wanted to see how much CO2 is producing every single process to produce 1 kilo of jewelry. And this, according to the process yield, because it's very common that in casting, factory that has 10, 20 people, they do not fulfill the burn-out furnace every day. Maybe they have burn-out furnace of 16 flasks, like the one that we were taking into consideration, and they just put 3 flasks. But the carbon footprint is the same, so 15 kilo of CO2 produced. So we were using the Eco Invent database. There were every single phase the calculation to do to calculate the quantity of CO2. At the end, I was expecting something better. But really also the 3D metal printing is not so green as I expected. You can see here, it's lower, but not much lower. I would say that in case of casting, we should stay at this process yield, because main companies, they less use the production capacity of their equipment. We got to conclusion this summer. Oh, I have 5 minutes.
You're good.
No, I was going faster. So no line. So we were doing something like giving marks for every single characteristic that we were benchmarking. And you see here our radar. We start from versatility of materials. Of course, here the winner, the technology that is much more versatile is 3D metal printing, since you can print in the same printer. Of course, if you clean. So you have to print, as I said before, titanium, gold alloy, platinum alloy, steel, or cobalt, chrome, whatever is the metal that you like, you can. Except, I think silver is not something very sexy for 3D metal printing. Or copper alloy is quite tough. Flexibility of geometries, I still say that, in my opinion, the advantage to make that hollow parts, to play with volume, to not making angry the designer that they want to do something, but the production say no, it's too heavy, or the sales say no, it's too heavy, then is any more a problem, because you can tune the volume and tune the weight. The surface quality always, in terms of roughness, traditional casting is still the best. We have a chance to improve, but at the moment, I mean, having a big power laser, having a spot much smaller, being able to make a trace much thinner, having powder flow instead, like the one we were using, from 0 up to 50 micron, have the cut 10, 20 micron, then for sure the roughness is going down drastically. But it takes time to really investigate. But really, at the moment, not really need for all pieces. Some pieces with no decoration, never mind if they are very rough. About definition or resolution, I would say that 3D metal printing is equal to direct casting. I don't see, we were also presenting a paper a few years ago where we compared exactly the two technology. We were doing a very deep investigation on the size of every single element we were doing on rose gold and platinum, and I will say again, it's not more rough. And of course, I didn't put casting because in my opinion, definition is also the ability to copy something. And if casting, traditional casting is not going down to 0.2 millimeter, sometimes it's not possible to reproduce that part or that detail. About defects, even if it's not important, 3D metal printing is the one that has the lowest defect in terms of metal defects. Mechanical properties, I would say, are similar, nothing different. Someone that is working 3D printed parts do not feel really the difference. Production capacity, traditional casting is the technology to use when you need to produce a lot, for sure. About lead time and small batches, 3D metal printing, as I said before, up to 20, 25 pieces. And lead time for the series, traditional casting, and eco-friendly sustainability is 3D metal printing. So, I wanted to say again about this Geoffrey diagram. People ask me, is the technology ready? Very often, is ready. I would say, are the people ready? That's the question. Yeah, because for sure, we have not to pass this point. We have to stay here, because then those people, the self-convinced people, are the one that helps us to tune, to do better the things that we are doing, because they see the glass. Half full, okay? They do not see the glass half empty, as usually those people that are much more pragmatic, they want results, they want use directly in production. But, and I believe that is a cultural reason. After I was in Paris, a few months ago I was in Paris with my wife, and we were at the Louvre Museum, okay? And I was doing the picture, and I was in front of the entrance, no line. The difference between me and those people was that I was doing a ticket online 1 hour before, in 2 minutes. Because sometimes the line comes in that way. So the question is, for what reason those people didn't make the ticket online? So they prefer to stay hours online, but they have another chance. So we have not to go to that people to tell that internet works. They will arrive. So, but I believe, I believe that people in this room should be on this side of the Geoffrey diagram. And it's like a baby. I keep saying it's like a baby. You cannot expect that the baby is not crying tonight. It's normal it's crying tonight. So if the printer is not giving you whatever you like, then it's normal. It's a baby technology. Few pictures, and I wanted to put this one because we recently printed and it's really awesome. If it's the right word. I love the detail and the resolution. Here, there is no Photoshop. We don't like Photoshop. I hope that we have the trust from your side that we are people that like to say we are wrong, but when we say something, it's because we believe. We have so much passion in what we do, and when I said I saw things, I cried because it's so nice and so beautiful, and said I want to put and show to the people doing the presentation. Here we have some rose gold, yellow gold. Then some hollow parts. and we did cross-section just for demonstration. And this is the Bangor in platinum, the one that we were printing in the movie in the beginning. This is a kind of geometry that makes us pretty. There is no sockets. It's all self-supporting, and this is nice. This is our dream. So, a company full of printers, okay, because we believe it's possible. When I go to a company doing chain, I say, Michael, be stupid, you have to do the same. Special thanks to my colleague that are helping me very much in this presentation. Very good thanks to them. And to Santa Fe Symposium people, so to Jessica, to Janet, to Eddie, to Mark, to Trevor, to Adam, and you know who is the next? You remember? A lovely thanks to my wife, that is supporting me very much and understanding when I stay up in the night to finish my presentation. So thank you very much.
Okay, so we'll bring the labels